Okay, this is the second lecture in Calculus 2. In the previous one, we looked at how to take some sort of a region, and let's say the region looked like this, for example, and go all the way, take this region and revolve it around the x-axis and back up the other side, and you get some sort of an object. And the way we did it was we said, okay, let's find the volume of each one of these little disks and go all the way around and go back up the other side, and we'll add them all up, and we got a formula that looked like this. From A to B. This is A and there's B. Okay, so that's fine. One thing I didn't mention is that you can also, there's nothing privileged about using the x-axis. You can also use this going around the y-axis. If you had an object, as I say, kind of like this one, and you wanted to go around the y-axis, you could do the same thing. Instead of writing this as a function of x, you would write it as some sort of a function of y instead. X as a function of y, this would be a little dy right there, and then you do the same sort of thing. You take that all the way around, go back the other side, and you'd have that. So I didn't do any of those, but those are also opportunities for you. But suppose we have, instead of something like that, suppose we have a function like this, for example, from A to B, and we want to take this region, the region under this function here. Here's f of x, all the way around the x-axis. Oh, I'm sorry, all the way around the y-axis. Okay, so it goes all the way around the y-axis. Can you imagine what it's going to look like? It's going to be this big thing. It's going to go all the way around. It's going to have a hole in the middle right there. There'll be a hole in the middle. It'll look kind of like an angel food cake that's slopped a little bit. And so that's what you're going to get, or a devil's food cake. And we want that volume. Okay, so that's what we're going to do today. And let me say, by way of kind of explanation here, the most important thing of this chapter is not just to learn these various formulas of how to do these particular things, but instead it's to learn the whole idea of how you can add up these infinitesimal things using integration to get the answer that you want. I really learned this. I'm a physics major as well as a math major in college, so when I was in physics, after having taken Calc 2, we had this problem here. What's the force on this point right here due to this electron right here? Here's an electron, here's an electron, and Coulomb's law, I think it is, says that the force is proportional to the values of the charges, the product of the charges divided by the square of the distance. Okay, if this distance is d, then it's the square of the distance, and that gives you the force. And if you want to find the force on this thing due to several charges, then you can basically just add up the force. You're going to have to think of them, realize they're vectors, of course, but add up those forces due to each one of these and add them together, and you'll get the entire force on this. So that's fine. You can do that without calculus. But then the instructor said, what happens if you have a wire here, a whole line of charge, and you want to find the force on this thing due to this whole line? Okay, well then you've got an infinite number of little points along here. So the way we did that was we took a little tiny portion of it, and we said, what's the charge in that little tiny portion, infinitesimal portion, and then we found the force on this thing due to this little portion, and then maybe this, I didn't do that very well, this is some little angle difference right there, and then we added up all of those as the angle went from, say, negative pi over 2 to pi over 2. And by doing that, you're getting the force all the way along from this entire line. And so that's the kind of thing that physicists, as an example, use this sort of thing for a lot. What's the moment of inertia of something which is spinning? All kinds of things like that. This is exactly the method that they use. And so we're doing some of them here in class that are kind of easier to visualize, such as volumes. but this is used in a host of different ways. So anyway, let's go back to this one then. So what's the volume that you would get by taking this thing around the y-axis? Notice I can't write it as a function of y because it's not one-to-one, so I have to use some other method to do it. So what could I do? Actually, I could break this up into various functions and do it, but anyway, I still want to show you another method. So here's what we do. Instead of making little disks like we made last time, we're now going to start off with the same little rectangle that we had before. Here's our little rectangle. Right there. It's positioned at the point x. The height of it, of course, is going to be f of x. And now we're going to take that little rectangle, instead of going around the x-axis, we're going to take that thing and go around the y-axis. Okay, so before I even tell you, you visualize in your own mind what kind of an object are you going to get by taking that little critter right there, that little rectangle, and going all the way around the y-axis and all the way back the other side. Okay, this really relies on you being able to imagine it. Do you agree you're going to get a shell? Okay, here I went to my bathroom and found this. Unfortunately, I only have two extremes. There's the other one. I wish I had one with just a little toilet paper, but I just put a new roll on this morning. Okay, too much information. But anyway, we'll use this one as an example because this is going to be a tiny little dx. We'll call that a tiny little dx right there. That's the width of it. It's positioned at x, but the width of it is dx. So what's going to be the volume that you get by taking this thing here and going all the way around the axis and back the other side? Well, remember what I said, that any volume is going to need three different dimensions. So what you can do is you can take this thing, first of all, this distance right there would correspond to this distance right here, right? It's the radius from there to there. So from here to here is the radius of this cylinder. You're going to get a cylinder, and the radius of the bottom of it. Okay, let me turn that right. Okay, the radius of the bottom of it is going to be from here to here, which is going to be x, taking that all the way around. So that corresponds to this distance right here. And then the height of it, that's going to be this distance right there. There's the height. And then finally the thickness, that's going to be just the thickness of this cardboard right there. Agreed? So if I wanted to find out what's the volume of this piece of paper right here, which is in the shape of a cylinder, maybe the easiest way to do it is just to cut it. And form a rectangle out of it, a solid rectangle, and it has some thickness to it, and then realize that the volume of this thing is going to be, first of all, the height of this rectangle. The height is just going to be f of x. Then this length of the rectangle, which corresponds to this length all the way around. And that length all the way around is going to be the circumference of a circle, 2 pi. And the radius of this circle is the distance from here to here, 2 pi x. There's the distance around. And then finally the thickness of it. There's the thickness of it right there, which is just your little delta x. Okay? So you add up all those things for every one of these rectangles going from here to here, and you're going to get an approximation for the volume. And then as before, the actual volume is going to be the limit of that as delta x goes to 0. And as before, that turns the thing into an integral. The 2 pi is a constant again, so that can come out front. we're adding up all these contributions as x goes from a to b. This x is not a variable, so that has to stay inside there. Here's your f of x, and then this, of course, becomes dx. So there's the volume right there. That you get by going all the way around the y-axis. Okay, and again, you can just let's take the same example we had before. I think we had what, from y equals x squared from 1 to 3. And if you take this thing around the y-axis now, take this region around it, it's going to be what? 2 pi times the integral from 1 to 3. The integral of x times the function is x squared, dx, easy enough to 2, it's going to be 2 pi. This is x cubed. The antiderivative of x cubed is 1/4 x to the 4th from 1 to 3. And you want to finish it off, so it's going to be pi over 2. And then 3 to the 4th, which is 9 times 9, which is 81, minus 1 to the 4th, which is 1, which is 80. 80 over 2 is 40. Going to be 40 pi. That worked out kind of nice. Okay, so there's your solid. That's the volume of the solid that you get by taking this region around. Okay. So as I did with the disk method, you should also be able to extend this to other kinds of situations. So, for example, what if instead of going around the y-axis, what if you went around the line x equals -3? Okay, so now I'm going to take this whole region here, and I'm not going to revolve it around the y-axis, but I'm going to revolve it around this line. So it's going to go all the way around that line, back the other side, and get yourself a big solid. And what's the volume of that solid? Okay, and again, I'd encourage you to go ahead and turn the video off for a moment and see if you can figure it out on your own. Okay, I can't remember, I haven't told you this class yet or not, but my whole theory of teaching, I learned from my 5th grade teacher, is that if I explain something to you that you haven't had a chance to think of before, it just kind of hits you, a little bit of it seeps in, but most of it just kind of runs off the sides of your brain. Okay, there's your brain right there. On the other hand, if you've wrestled with it and tried to figure it out on your own, you've effectively made a little divot in your brain right there, and now when you get the right answer, you get this really nice aha feeling. Ah, that's it. The best thing is if you actually figure it out for yourself, but if you don't, you've wrestled with it, and now when you see the answer, you absorb it because you've developed a spot in your own thinking to place it. Okay? And you also, if you don't figure it out, it shows you that you still don't fully understand the material. So that's good stuff to know too. Okay? So anyway, let's go back to this now again. Here we go. We want to go all the way around. So let's think of what's a little volume going to be, a little dV. What's the volume that you're going to get by taking this region here all the way around? It's going to be the height of it, which is f of x. It's going to be the distance around. But if this point is x, now the length of this radius is now going to be x plus 3. So it's going to be, this should have 2 pi there. So it should be an x plus 3 times 2 pi. That gives you the distance, that gives you the circumference. 2 pi times the radius. Here's the radius times 2 pi. That gives you the circumference. That gives you the height. And now we finally have a little dx for the thickness of it. And you add all those things up. The 2 pi can come out front. X plus 3, f of x, dx from A to B. Okay? So there are various kinds of problems you can do like that, just to make sure you understand what's going on. Okay, I'll let you figure out what happens if you have two functions here. Oh, heck, again. Let's just do it together. Easy enough to do. Let's say that you have two functions here. So here's f right here, and here's g right there. And here's your x-axis, and you want to go from A to B right there. And you want the volume that you get by taking this region around the y-axis. What would it be? Okay, again, turn off the video for a moment if you need to. Okay, I'm assuming you're back on. So I'd say, well, let's see, at some point x, right there, I'm taking this little region all the way around. The height of this is going to be f of x minus g of x. I multiply that by the distance around, which is going to be 2 pi times x. There's your circumference. And then finally, you multiply that by the thickness, which is dx. And you add up all those things again from A to B. There you're all set. Okay, so again, don't memorize the formula. Understand it. Understand it. Okay, that's what we're after here. Okay, so let's go ahead and use this method to do the two problems that we ended last time with. Let's find the volume of a cone and also the volume of a sphere. So here's a cone. The height of it is h, and the radius here is r. So we want to use the cylinder method. Call this the cylinder method. A lot of authors call it the shell method, but we're making little cylinders rather than shells. I don't know how they get the word shell out of what this thing here is not a shell. It's a cylinder. Okay. So anyway, we need to start off by thinking of what kind of an object, what kind of a function do we need in order to use this method to generate a solid like that. And again, I'd encourage you, turn this thing off, do it on your own. If you watch me do it, you shake your head yes, that means you know it about 40%. Okay? If you shake your head no, I don't understand, then you're admitting, at least to yourself, you know it 0%. But in order to understand you know it 100%, you have to be able to do it on your own, not just watch me. Okay? So take a moment, try to figure it out on your own. Okay, I'll get a cup of coffee while you do that. Okay, I had my coffee. Hopefully you did it. Let's go ahead and do it. So here's what you want, something like this. And so we're going to take this all the way around. This is going to be your R right here. This is going to be 0h right there. So the equation of that line is going to be h, and then the slope of it is going to be, there's your y-intercept. The slope is going to be what? Minus rise over run, which is what? Minus h over rx. You can use whatever method you need. You got 2 points on it, however you want to show that that's the equation of that line. That's all 9th and 10th grade stuff, okay? So you should know that coming in. Rise over run. Very good. Okay, so there it is. So now what's the volume going to be? It's going to be 2 pi times x times the function from, we're adding up all these contributions from 0 to r, like that. And now we're going to get 2 pi. Now we're going to get hx minus h over rx squared dx from 0 to r. Now we're going to get 2 pi. But I'm going to do a couple steps in one. I'm going to go ahead and take the antiderivative. The antiderivative is x squared over 2. So it's going to be h over 2 x squared. Antiderivative of this is going to be what? H over r. Antiderivative of x squared is x cubed over 3. So you have that right there. Evaluate that from 0 to r. What do we get? I'm going to run out of room here. We get 2 pi. Notice that when I stick in 0 here, I get zeros both places, so all I have to worry about is putting in r. Here I'm going to get r squared h over 2. Just write it down here. R squared h over 2. And here, when I stick in an r, I'm going to get r cubed over r, which is r squared h over 3. So there's r squared h over 3. So if you have half of something minus a third of something, that's 3/6 minus 2/6, which is 1/6. So you end up with 1/6 r squared h. And by the time you multiply that through, you're going to, whoops, r squared h. And you multiply that through, and you're going to get what? Pi over 3 r squared h, which is the same thing that we got last time. And again, let me make sure that I'm still recording. Yep, I am. Very good. Okay, there it is. Okay, let's also do the sphere again. Let's see, what time is it? Okay, very good. The sphere, remember what, in the last one we found the equation of the sphere. The equation of the sphere is going to be what? Y is equal to a radius r, square root of r squared minus x squared. And notice I'm not even doing this portion right here, because I'm going to take this portion and go all the way around the other side. Here's your y-axis. All the way around the y-axis and back to the other side. Okay, so here we go. The volume is going to be 2 pi times x times the function right there, r squared minus x squared dx. And we want to go from 0 to r. And if you take this whole region here all the way around the other side, you're going to get exactly half of the sphere. We want the whole sphere, so again we'll use symmetry, and we'll multiply this by 2. If you multiply it by 2, you're going to get a 4 out there. So there's what we have to integrate. Okay? This one goes back to something that we learned at the end of Calc 1. How do you solve something like this? You use what's called the Sub Method of Substitution. You let u be equal to r squared minus x squared, and then du is going to be 2r dr. Remember that? So you look for something in there which is really bothering you. I don't know how to handle that, so I'm going to let u be the whole thing. And then the only way this will work is if the derivative of this is out there that you can use. So sure enough, the derivative of this is, oh, I'm sorry, totally wrong. This is all with respect to x. Du is going to be the derivative of r is 0. Did you catch that mistake? The derivative of r is 0. The derivative of negative x squared is going to be negative 2x dx. I don't think I've ever done that before in my life, okay? And now it's on video, but I'm not going to take time to erase it, okay? There it is. So there you are. So there's your u, and hopefully you got a du. Let's see once what happens. So it's going to be 4 pi. So this all becomes the square root of u right there. That handles this. Now notice we have x dx left. X dx is equal to minus 1/2. So I'll bring the negative 1/2 out front. Times, x dx is equal to negative 1/2. Let's just write it like this. Negative 1/2 du. So there's my du. Here's my negative 1/2. And now, what are the new limits of integration? You have to change the dummy variable. When x is equal to 0, u is going to become r squared. And when x is equal to r, when x, the dummy variable here, is equal to r, you're going to get r squared minus r squared is 0. So you're going to get that. Okay, so that's what we need to evaluate. I'm going to make things a whole lot easier. By first of all, 4 over 2 is 2, so I'm going to write this as 2 pi. Look at all the things I did here. First of all, I wrote the square root of u as u to the 1/2. Secondly, I somehow got rid of that negative sign. That's not a mistake. I got rid of it. How did I get rid of it? Aha! I changed the limits of integration. If you flip it, remember, the integral from a to b is the negative of the integral from b to a. So that makes things easier. I don't want any more negatives in my life than I have to have. So I get that right there. Now I think we can go ahead and solve it. You're going to get 2 pi. Now you're going to get the antiderivative of this. Antiderivative of u to the 1/2 is u to the 3/2 divided by 3/2, which is the same as multiplied by 2/3, all from 0 to r squared. So I have 2 times 2 is 4 pi over 3. The square root of r squared is r. That's going to give you r cubed. Boom, right there. Stick in a 0, you get a 0. So there's the volume of a sphere. Okay, good job. So, I'm going to leave you with one problem that I'm not going to do, but it's kind of a nice one. Okay, and I'm not going to do it because any of you watching should have some opportunity to try it on your own, and all of my students who are going to be using these should have an opportunity to do it on their own. What if instead of a circle, what if we use an ellipse instead? There's the equation of an ellipse. It's a circle that's been squashed one way or another. If they're both a and b are positive. If you make a bigger than b, then it's going to be long and squashed. It's going to look like this. Okay? So this is a right here. Here's negative a. Here's b, and here's negative b. The way I remember that is, I just say it's basically the same as the equation of a circle. If you divide by r squared there, you get this. So there's the equation of a circle of radius r, and this is the same sort of thing, except you've squished it so that it's not the same in the y direction as it is in the x direction. But notice that if y is equal to 0, that means you're on the x-axis. If y is equal to 0, then the two values which make it true are going to be a and negative a. So there's your r. If x is equal to 0, which means you're on the y-axis, then the two values that make it true are b and negative b. So there's where you are. So there's the equation of an ellipse right there. So here's the question I'll leave you with. Using either method, the disk method of last time or the cylinder method from this time, find the volume of revolution by taking it around the y-axis, the x-axis or the y-axis. Okay? If you exaggerate this even a little bit more, shouldn't say exaggerate, you just make your A a lot bigger than your B, you can see that the volume that you get by going around the x-axis is not necessarily going to be the same. There's no reason to think it's going to be the same as the volume you get by going around the y-axis. The circle, the sphere it was. Here it's not. This way here gives you something like a hot dog. Agreed? Going around the y-axis, this is around the x-axis. Going around the y-axis is going to give you something like a hamburger. Agreed? So go ahead, and here's the challenge. Try to do both. Try to do this problem. Find both of these things using both methods. Use the cylinder method, and also from last time use the disk method. Find the volumes going around the x-axis and also going around the y-axis. And here's what you know for sure. You know that whatever answer you get had better turn into this answer when a is equal to b, right? If a is equal to b, which we can then call r, it had better give you this, because that's then your sphere. So that's one way to check it out. In fact, I'm not going to tell you anything more. I'm going to turn off the video before I'm tempted to tell you the answer. Okay, so see what you can find. Okay, very good. Next time we get into lengths of curves, okay, which is a cool subject.